Welcome back, guys. Hope you had a great February weekend. Nova and I were a little bit bored, so we thought we would make a new video on us playing Uno. So, let's see who's going to win, Nova or myself. Alright, here we go. Okay, Nova, Nova, I don't want to see your cards. Can you please put your cards away so I don't see them? No. Okay, let's reshuffle, alright? Okay. +2, Nova. Are you absolutely... I know you're hiding. +2. Okay, I'll pick up +2 cards, okay? And then I'm going to play one and then it's your shot again. Honestly. Nova, you can't play a green card when you said you wanted to change it to red. What's that? Oh, you're colourblind. Oh, okay. Right. So let's take that back and then let's start again. But this time you need to make sure you play the right colour, okay? Right colour, please. Okay. Nova, why are you giving me a paw? Oh, because you can't say Uno. Right, okay, fair enough. Okay, so your last card is now. Well done, Nova. That's your winning bone and your winning card. Maybe we should try Monopoly next time? National 5, just a little bit of fun there with Nova and Uno. But now it's time to move on to recapping the whole topic of properties of matter. We've spent 4 weeks going through it. I hope it's been okay. There is some difficult bits on it, so I'm going to go through it all now. And hopefully it makes a little bit more sense. And then we'll be doing some past paper questions that will really help drive home this topic. So, like, share and subscribe, guys. Just to let you know as a side note, we're actually very close to 300 subscribers. So keep on liking, sharing and clicking that bell. Now, properties of matter revision. So today's lesson we're going to cover 5 things, okay? We're going to cover pressure, force and area, Kelvin scale and volume, pressure volume law, pressure temperature law and temperature volume law, okay? So let's first of all look at pressure, force and area. Okay, now again, I'm not going to be looking at worked examples, any of that. They have been in the other videos, particularly the gas laws worked examples. I've given a whole other video to that. So this is just going to be for the theory. So examples to consider when we're talking about pressure, force and area. Remember, when we, for example, pushing a drawing pin, we have a flat side and we have a very pointy side. It's all based on area. Something with a large area is going to have a very small pressure. Something with a very small area is going to have a very high pressure. Okay, if you were to press down on a pin with a flat side, it's not going to hurt. If you were to press in with a pin side, it's going to hurt a lot, and it's down to the area of something. Okay, like heels and flat shoes. Heels have a very small area and therefore has high pressure, and same idea with large area means low pressure. Okay, so if we were to look at this here, and it never seems to come out right, so I do apologise for this, it never ever seems to come out right, but it's meant to be P equals F divided by A, so that F is meant to be divided by A. Okay, pressure is measured in pascals, force is measured in newtons, and area is measured in meters squared. Okay, so please, the biggest thing throughout all my classes has been conversion of units. Okay, for area, you must put it into meters. Okay, you must put it into meters, otherwise it will not work. It's because units of pressure is pascals, but pascals is a newtons per meter squared, not centimeter squared per meter squared. So you need to get that right. Okay, so for example, this is the classic example where you'd have to do almost three full things. Okay, so it says a 0.5 kilogram steel cylinder of radius 10 centimeters is placed on a bench as shown. Calculate the pressure exerted. Okay, and then we've got that weird diagram there. So this is how you would answer it. You use your equation, P equals F over A. Alright, how do you find the force? Well, if you've got something lying on something, then there's going to be a weight pulling it down. So then we do W equals mg. So W equals mg is going to be 0.5 times 9.8, because 9.8 is the gravitational field strength, 0.5 is the mass. You get 4.9, I insert that into F. Then I find the area. In this case, is a cylinder, so a circle means pi r squared. I figure that out, I put that into the area. Now, if a question asks for maximum pressure, you need to then obviously find the smallest area. So sometimes it might have a cube and it says, or a cuboid or whatever, and it says, what is the maximum pressure? You're going to have to find the smallest area, okay, and do length times breadth, and then insert that into P equals F over A. If it's for minimum pressure, you're going to have to find the largest area, okay? And remember, that's in pascals. So that is an example there. Now, Kelvin scale and volume, number 2. So, for this one here, how many centimetres cubed rather than metre? 1 metre cubed, okay? The only reason we're finding out volume is that, and we're going to come on to this later, is that we need to know that how many centimetres are in a metre and how many centimetres cubed are in a metres cubed. And it actually turns out that there's 1,000,000 centimetres cubed in 1 metre cubed, and you can see the working there. Now, I'm not going to get too bogged down by this because something happens later that, again, lots of people have been getting wrong, okay? So, temperature. The temperature scale, okay, or is the Kelvin scale, and that's the one we've been using in gas laws. This is such an important temperature scale to use. Celsius is no longer something that we use in the gas laws. It's only the Kelvin temperature. So to get into Kelvin temperature, and I've shown you this slide many times, it's the Celsius temperature plus 273 degrees, Celsius temperature plus 273. So to get to the Kelvin, you must always add 273. So the Kelvin temperature must be bigger than the Celsius temperature. And the smallest temperature possible in the universe is 0 Kelvin. 0 Kelvin is the equivalent to minus 273 degrees Celsius. Okay? So, note that any change in temperature, remember this equation, EH equals Cm delta T, any change in temperature in Kelvin is the same as the change in temperature in degrees Celsius. So changing 10 degrees Celsius is the same as changing 10 degrees Kelvin. We said that last time. Now, this is again just a completed table of the work that we did 2 or 3 weeks ago now. So you should see that the temperature scale is always less than the Kelvin scale. So the Kelvin scale should always be bigger than the temperature scale, and you're always adding 273 from the temperature to get from Celsius to get to Kelvin. Okay? So we should be aware of that now. Please, please, please. So then we moved on to the gas laws, and number 3 was the pressure and volume. Okay, and we're going to look at the kinetic theory. So pressure and volume law, we said that take a kind of syringe, reduce the volume, what happens to the pressure inside that syringe? Well, I'm going to move on here because this is the important slide. We talked about the kinetic theory. Now, the kinetic theory is talking about what happens to the particles in the object. So for this one here, as the volume decreases, the particles collide more frequently with the walls, just as it would be if you were to put 20 pupils in a classroom and then move them into a cupboard. Okay, it would be there'd be a very little space for people to move around, so they'd bump into each other more. So particles collide more frequently with the walls. Therefore, there's going to be an increase in the average force. And if there's an increase in the average force, the pressure will increase due to P equals F over A. Now, throughout this, we are keeping temperature constant. See, the constant temperature. So the only thing we're doing is pressure and volume. Why? Because then we get to the equation, and the equation looks like this here. P1V1 equals P2V2. P1V1 equals P2V2. So this is the first equation. You must memorize these equations that I am showing you now because they're not in the equation sheet, but P1V1 equals P2V2. All right? So the kinetic theory is explained down there just as I explained moments ago, but I'm going to go back up to this slide here because there's 2 graphs here. The 2 graphs. One is looking at P over V, and the other is looking at P over 1 over V. Now, when you increase volume, you will decrease pressure. Makes sense. If you have a syringe, if you push it out, then it's going to have increased volume and you're going to have less pressure. But when you decrease the volume, then you're going to have an increase in pressure. And that just makes sense. So that's why it looks like a curve. But if we wanted a nice straight line, because it's an inversely proportional, which means that when one thing gets bigger, the other thing gets smaller. Therefore, you need to have P on the y-axis, 1 over V on the x-axis, and that would get you a straight line through the origin. Now, these graphs are very important for multiple choice questions because they come up time and time again, so you need to be careful of the labels and the axes. Okay? So that's all summarised in this slide here, a very important slide actually, that has all the things I have just said, but if you're ever wanting to look at this, pause it, take a photo of it, or keep it handy, but this is the most important slide. I've got one for each of the gas laws. Make sure you know what's on this slide. Okay? Right. Next one is the pressure, temperature, and kinetic theory. Okay, not very well formatted, that one. So for this one, again, we have a small temperature. We are keeping, because it's pressure temperature, we're keeping the volume constant. Volume is not changing here. So when you see this, you can see that the syringe is still at the same position, but this time the temperature has increased and the particles are going to be moving much, much faster. Okay, basically, the kinetic theory with this is as temperature increases, the gas particles speed up. Particles will then strike the container walls more frequently because they're faster with greater force. Okay, because they're obviously going faster. Think of a ball. If you were hit with a ball, a slow ball, it wouldn't be that hard, it wouldn't be that sore. But if you were hit with a ball with faster, then it would be quite sore. Okay, so when that increased force will then increase the pressure due to P equals F over A. That is the kinetic theory. Okay. So remember the equations for this one, or for the graphs for this one, you've got pressure against temperature. This is why we do not use degrees Celsius, because degrees Celsius has this odd looking shape at the top, whereas if we have it in Kelvin, we know that 0 Kelvin is the smallest temperature, so anything from 0, it goes as a straight line through the origin, okay? And for degrees Celsius, if you were to extend that line back, it would go back to minus 273 degrees Celsius, okay? So that's very, very important. So if you were to double degrees Celsius, that's not going to be the same as doubling in the Kelvin scale. Okay, so just be very careful of that. So again, P1, this one is, remember, no volume because volume is constant. So this is P1 over T1 equals P2 over T2. So that's P1 over T1 equals P2 over T2. Again, the format's not great. And the kinetic theory is exactly how I've said it before. And again, a very important slide is this one here. So if you want to pause it, you can pause it and take a note of that. Okay? So that's the fourth one. The last and final one is volume and temperature. Okay? So the volume temperature law, remember now, is keeping pressure the same. So pressure is going to be constant. So if you were to increase temperature, so going from 20 degrees up to 50 degrees, the syringe, as you see here, has moved from being close to now being further out. Okay? So as the temperature increases, the speed of the particles increases. So speed, as I've said, remember, they get faster, the speed increases. So therefore, there's more collisions with the container wall, and therefore there's more force. But to maintain that constant pressure, the volume must increase. Okay? This is kind of, again, why I've talked about the deodorant can. If you increase pressure, if you increase temperature, the pressure will increase in a deodorant can and then explode. Theoretically, that's because the volume wants to increase. Okay, so in this one, pressure is the same, so what has to change? The volume changes and it becomes bigger. So if we were to look at the, again, the graphs for that, we've got volume against temperature for the degrees Celsius is exactly the same as the last one. And we'll prefer the one with Kelvin because it has a nice straight line through the origin. Okay, so you must make sure you remember these graphs. I cannot express that enough. Right, and remember this is directly proportional in temperature with the Kelvin scale. So again, format's not great, so I might just go to the very bottom one. Actually, yeah, there we go. V1 over T1 equals V2 over T2. That's extremely important. V1 over T1 equals V2 over T2. So if you have something that only has volume and temperature, then that would be, you would have to use this equation here. Okay? Now, this is the final equation, okay, which is PV over T equals constant. That is the equation you'll see in your equation sheets. Now this means that, as you've done last week, there is an equation that sometimes you need to use when you get given 5 pieces of information. That's P1 V1 over T1 equals P2 V2 over T2. This is basically this one here, but with another P1 V1 and T1, okay, equals P2 V2 and T2, rather than the constant being there. But this is the one that you'll see in the equation sheet. So that's why I've told you to go away and memorise those 4 equations. Now, I have done a separate video on this for the examples, which is very, very important, that goes through each of these equations. So P1 V1 equals P2 V2, V1 over T1 equals V2 over T2, P1 over T1 equals P2 over T2, and the last one, which is P1 V1 over T1 equals P2 V2 over T2. All of those ones I have given examples on, so please go and look at those examples. Very, very important you do that if you're not sure what's going on here. Lastly, okay, just to finish, people are getting mixed up with changing from centimeters cubed into meters cubed. Please do not worry about that, okay? Keep it in centimeters cubed as long as you keep the final answer in centimeters cubed. Why does it not matter? Because it's just a prefix. It's not like a Kelvin scale and a degrees Celsius scale where it changes the answer. It's okay to keep it in centimeters cubed, and I would tell you now, do not complicate life for yourself. Keep it in centimeters cubed. All right, so that is everything there. As I said, I've got an examples video that is a very, very good one for looking at how to do all the questions. Hope that helps. Hope that's all the information you will need, and that the past papers are very easy and that you understand the work. So very well done, National 5, and I hope you have a good week.